Okay, so to find a second derivative of a parametric function,
I have one question.
we're going to begin with our two parametrics. And we're going for our second derivative here. To find our first derivative, dy dx, we're going to take the derivative of each of these. Yes?
What's a parametric?
Parametric means we have two separate functions, one defining the x motion of a particle and one defining the y motion of a particle. So the first equation is telling us that any given time, t stands for time, where is this thing horizontally along the number line? And the second equation, y, tells us where is it vertically along the number line. And when we combine those, this thing could be moving then in any direction at any given time.
So do derivatives and second derivatives still tell us the same thing, like slope and cavity?
Yep, since we're taking in terms of the dy dx, then yeah, they still tell us slope and concavity. So we start by taking the individual x derivative in terms of t, so 1 minus 2t, and the y derivative in terms of t, 1 minus 3t squared. Then if I want dy dx, I need to take the y derivative and divide it by the x derivative. Those dt's would cancel, so we would just get dy dx is the y derivative divided by the x derivative. So that's a review of something we did back in chapter 3. New then is how we take the second derivative of this thing. If I want the second derivative of y in terms of x again, what we are going to do is take the derivative of our last answer. I wrote that wrong. The derivative of our last answer, but we have to take it in terms of t because that's what's in the problem. But I don't want this thing in terms of t, I want it in terms of x. So we're going to divide again by another dx dt. Okay? So we're going to take the derivative of our last answer the way we usually take a second derivative. But since there's no x's in there, I would have to take that derivative in terms of t. But I don't want it in terms of t because I'm asked for the second derivative of y in terms of x again, dx2. Okay? So I'm going to take the derivative of that last answer in terms of t, since there's t's in it, and then I'm going to divide it by a dx dt so those dt's would cancel. And it will be in terms of x then again. So to take the second derivative of this thing, I need a quotient rule. So low d high minus high d low over low low.
What's dt?
dt is just that we're taking it in terms of t. Then I'm going to divide this by the original dx dt. Yes?
Why do we divide it by dx dt?
Because when we just took the derivative of dy dx, we took it in terms of t. But what we're asked for has nothing about t's. It's not the second derivative of y in terms of t. It's in terms of x again. So we need to divide by dx dt to cancel out the notation of the dt.
So when it's dy dx over dt, that just means it's the derivative, but with t's as the variable.
Right. Yep. So we could do some algebra to kind of clean this thing up a little bit. On the top, I'm going to do some distributing. So I'm going to get negative 6t plus 12t squared. And then here I'm going to distribute a negative 2 and a negative. So it's going to give me plus 2 minus 6t squared. Now dividing by this 1 minus 2t is the same thing as multiplying by the reciprocal of 1 minus 2t. So all going to be over 1 minus 2t cubed. Combine up some like terms, 6t squared minus 6t plus 2 over 1 minus 2t cubed. Right? So to find a second derivative, we find the derivative of our derivative, the way we would normally think about finding a second derivative, but since we took that derivative in terms of t and not in terms of x, we need to divide by the derivative in terms of x.
Why does that work?
Because notationally, what we've done, I wrote it with a prime, but we've really just found like d second y dx dt. We found the derivative of y
Oh, I see.
in terms of t, and we divide that by a dx dt, which cancels those dt's and puts the dx's together to give us what we want.
Yeah, that makes sense.
The notation gets pretty messy.
D2 is 1 minus 2t squared, or dt is 1 minus 2t
That's pretty
squared.
impressive.
We don't have any dt individually. Like we can't really separate the dt from it. Because dt is a part of each derivative here, really.
It's divided by dt and then the top's divided by 1 minus
When
2t.
it says divided by dt, that doesn't mean like a division, it means in terms of t. That we're letting t be the variable of the question.
So where'd you get 1 minus t, or 1 minus 2t squared from?
That's our quotient rule. Low d high minus high d low over low low. So that's the bottom squared.
I got that mixed up when I first did it. And then my answer was negative. And then it's
Yep.
You divide these dx divided by dt, but don't you need to do that in another side?
No, we don't need to do on the other side because we're fixing the notation so that this thing will end up being the second derivative of y in terms of x both times. So we're not, we actually have to do that just on the
okay,
one
I
side
see.
so that it matches what's already
I see.
on the other side. The notation gets really messy. So try not to get too hung up on the notation. The notation shows us why we're doing what we're doing, but the notation gets pretty messy. Let's try another example. If x is equal to the cosine of t, and y is equal to, we'll just make it sine of t. So to find our first derivative, we take the derivative of each of them individually in terms of t. The derivative of cosine is negative sine, and the derivative of sine
Cosine.
is cosine. So if I want dy dx, I take the y derivative and divide by the x derivative. I could leave it like this, but then when I take another derivative, I would need a quotient rule. So it'll make taking derivatives a little bit easier if we clean this up and make it negative cotangent of t. Now, if I want my second derivative, I'm going to take the derivative of this, so that is positive cosecant squared. Okay, the derivative of cotangent is negative cosecant squared, and since there's already a negative, that gives us a positive cosecant squared. We take the derivative of that and divide by the original x derivative. So this guy is going to make a reappearance down here now. Negative sine of t. Okay? And that's what fixes our notation so that we get that dx squared. Because otherwise, we're doing this thing in terms of t, so we have a dt and not another dx, which is really what we need, is another dx. So that's why we have to divide that down again. This would not be a multiple choice answer. What's the same thing as cosecant?
1 over sine.
1 over sine, so this is really like 1 over sine cubed or negative cosecant cubed. Okay. All right, so that is first and second derivatives of parametrics. Then we need to talk about the length of a parametric curve. Length of parametric curve is actually something we're concerned with quite often because what a parametric curve is usually defining for us is the motion of something. So if I find the length of that, then that's telling me how far that thing went. Okay? So that is something that we are often concerned with in a parametric. Back when we learned the arc length formula, which is hopefully still there somewhere, we learned that arc length is the integral from A to B, our two constraints, of the square root of, and then we had 1 for one of those things. And the reason why we had 1 was because we were taking our derivatives in terms of x or in terms of y. So dx is just 1. But if we're taking our derivatives in terms of t, they are both going to be something now. Okay? So this formula is exactly the same as it used to be, except before, one of these things was a derivative and one of them was just 1, because dx is 1, or dy is 1. Okay? Now they are both going to be something because they are both individual derivatives.
Is that usually the equation for a circle? Sort of.
I
Minus the
suppose
square
it's
root.
similar. Yeah. I mean, there's an integral in it. There's no integrals in a circle, but it's similar.
Yeah.
Remember this formula came from the Pythagorean theorem, and that's why we have the square root of stuff squared. Because if I'm looking for this length, and I know this length and this length, to find that, I would need the square root of the change in x squared and the change in y squared. And we would need to do this for lots and lots and lots of little baby triangles. So to do it for lots and lots and lots of little baby triangles, we integrate it and add them all up. Because that's what an integral does, is adds things up. So example 3 gives us a picture of, it's called an asteroid. The function that defines this is given parametrically. And it takes a full rotation of 0 to 2 pi to get the entire curve. So to find arc length, we need the individual derivatives. So the derivative of x is chain rule. 3, leave the inside alone, lower the power, times the derivative of the inside, which is negative sign. I threw the negative out front of everything there. And dy dt, again, chain rule. Bring the power down, leave the inside alone, times the derivative of the inside.
So on this one, the outside is the squared.
Yes, the outside is the cubed, yep.
Alright. But if it was on the other side of the t, then the outside would be cosine.
Yes. Yeah, if it was written as like cosine of t cubed, then it's assumed that it's the t that's cubed. So then the outside would be the cosine. Yep. All right, if we were taking a slope, we would then need to divide these. But we're going to take the length, so we want to actually keep them individual. Our length formula is going to integrate the square root of these things squared, okay, because it's coming from the Pythagorean theorem. So we have the square root of these things squared. If I square dx dt, squaring negative 3 makes positive 9. Cosine to the 4th and sine squared. And if I square the dy, I get 9 sine to the 4th and cosine squared. Now, if we integrate from 0 to 2 pi, we're going to run into a problem because sine and cosine give us the same answer at 0 and 2 pi because 0 and 2 pi are really the same value. So what we're going to do is integrate just one quadrant of it and multiply by 4. And that'll give us the full length of the curve. then we're not going to run into a problem. Because otherwise, if I'm integrating from 0 to 2 pi, I'm integrating really from a number to itself in terms of trig, and that will always just give us an answer of 0. So that would give us quite a problem here. There is some really nice stuff that happens inside of this messiness.
How is the cost?
Wait, go from 0 to pi over 2 or 0 to 2 pi?
0 to pi over 2, and I'm multiplying by 4.
I bet it equals 1.
Everything is easily squared, rooted.
That's true.
Yeah.
You can take the square root of a part of a sum. So yes, everything in there is easily square rooted, but you cannot take a square root of one part of a sum, because if you did that, think about like 9 plus 16, that would give 3 plus 4, which is 7, but if I actually did it, I'd get the square root of 25, which is 5, right? So that's a little bit of a problem. That's a no-no.
That's always true.
Yes.
You get that 4 because there's
Because there's 4 quadrants. Yep.
What is that called? I'm forgetting the name where you square root of things squared. Just what's that called?
I don't know.
That. How do you find the length?
Yes.
If the
Pythagorean theorem?
interval was more than
It's always true.
between 0 and 2 pi, so we have to
Easy to square
add
root.
the
You just
overlap,
square.
the digit.
Yeah.
If it went from more to 0 than 2 pi, like so if it went from 0 to 3
Yeah,
pi,
like that.
then yeah, yep, then I would just do like 6 sections of it instead of 4 sections of it. Yes,
She goes first.
yes.
So when there's sine and cosine, it goes to 0 to 2 pi, we always take the quotient.
Right, if we're working with trig functions and going from 0 to 2 pi, we need to break up that interval, because otherwise we're just going to get an answer of 0 always.
Is the all students take calculus like positives and negatives? Is that going to come into play here?
so if you were
No.
that would
Because we're talking about the length of the curve, and length we're always going to define as being a positive length. All right, so inside of here, there's some factoring that can be done. Both parts of this have a 9 and a cosine squared and a sine squared. If I take that out of the first one, it leaves a cosine squared. And out of the second one, it leaves a sine squared,
It's 1.
which is just 1. And now I don't have a sum anymore, so now I can take the square root of individual parts of a product. So I get 3 cosine t sine t.
It's a lot better what I was doing. Could erase what I was doing.
Now, unfortunately, the integration from here doesn't go great, because that's still not something that we really know how to integrate too well. So we would need to
Does our calculator
work on some substitutions or something like that. But at this part, we're just going to finite this guy.
Why, when it was 9 cosine squared t sine squared t, couldn't you put parentheses around the cosine squared 9 squared stuff, or is it 9 cosine?
Yeah, couldn't you take a 9 out of both of those and turn that into 1?
And then it's just 1.
Because there's no plus between them. It's cosine squared,
Oh.
sine squared. It's
Oh,
not
yeah.
cosine
that's
squared plus sine
multiplied,
squared.
okay.
They're multiplied.
oh
Those dang
yeah, they're not
T's.
multiplied.
Yeah, they're t's. They're t's, not pluses. Yes.
Couldn't you just put it to
I do that
1?
all the time.
Cosine squared
Easy
t plus
six.
sine squared plus 1.
That's one of our trig identities. That cosine squared plus sine squared is equal to 1. That's like the only trig identity that I've ever seen show up on an AP Calc test. There's a lot of trig identities, but that's the only one I've ever seen show up.
Have you learned this?
Can we spin into way earlier then? Instead of working on it right now?
Yeah, we could have finished it earlier. Typing that into the calculator would be a bit of a burden though, because there's so much going on in there that you're bound to end up with an error. But
Oh, not with my computer.
there's a whole lot of
Not
stuff
with my cast.
on there.
I feel like that only.
In the end, this thing turns out beautifully.
See?
I feel cheated.
Yeah.
I actually
I think
don't.
they should put the 4 0 to that on the clock at 6.
I actually don't. I actually
Like
don't.
Mr. Rohr's clock.
Yeah.
I actually do not feel cheated just because in order to get that 6, you already had to multiply something by 4 and 3, so which means you divide 4 by 3 in there, and it's actually not that pretty of a number.
Well,
which
good
is
luck
what
with
you
that.
expect from cosine.
Yeah.
I did it from 0 to 2 pi and it still gave me 6.
Nice.
Lucky? I don't know why it did, because sine and cosine at 0 and 2 pi, you're going to get the same answer. So you'll end up doing like something minus itself, which is 0. So I don't know why it gave you 6. That really surprises me.
How do I take these things in?
I almost feel like you typed it in wrong and got lucky.
You probably typed it in right if you got the right answer. I'm just surprised that the calculator gave you the right answer.
Wait, I'm confused because I typed in 9 times cosine of x squared times sine of x squared.
Mm-hmm.
I integrated that. Times 4, shouldn't that give me the same thing?
Yes,
It didn't.
I believe.
Yeah, no.
So I'm guessing we can use our calculators on this test?
Yes, for some of it.
I'm gonna have to borrow yours, mine won't
Is
turn
this
on.
cycloids now or is
Tiny
this
batteries.
another example?
Oh.
I think it broke.
Maybe someone
Are the batteries in the right way?
turn down your contrast.
Is this cycloids or another example?
This is cycloids. It's an example of cycloids.
I have one more quick question. Do you have a calculator that's pretty print if I ever need to borrow one?
No.
You don't.
What?
All right, let's
Try turning the contrast stuff or down.
let's do our last example, please. This question wants us to find the length of one arc of this curve. This particular curve is called a cycloid, and what happens when you graph it is it creates bumps like this that go on forever and ever and ever. So we're asked to find one bump of it.
Is that a -1 or a t in the x equals?
A t. For the x, it's a t. For the y, it's a 1. First, to get a feel for this thing, I would graph it out on the calculator with some different values of a. Like I would just plug in a is 1 and see what happens, or I'd plug in, a is 2 and see what happens. It turns out that all of the bumps are going to land at the same place, and what that a is going to do is make the curve either taller or shorter, but they're all still going to land at the same place, which is 2 pi. Okay, so it's going to take 0 to 2 pi to draw one arc, and all that a is going to do is make the arc either taller or shorter. Okay. So then if I want to find the length of this, I'm going to integrate from 0 to 2 pi. Here we have to go 0 to 2 pi because I guess we could go 0 to pi and break that up by 2 and double that. But it'll work okay to go 0 to 2 pi on this one because of the subtractions.
Can we go to 0 to 4 pi and have it?
Why would you?
I don't know. Why would we split it in half and double it?
Yeah, and this one.
Then we need, in our square root, the derivatives squared. So the derivative of x, that a is a constant, it can just hang out. And then the derivative of the inside, 1 minus cosine of t. And when we put that into arc length, we need to square it. Plus the derivative of y, a is a constant, it can just hang out. And then when we put it into arc length, we need to square it.
These are so much better.
There's a lot of trig identity stuff that can happen in this, and we're not gonna do it. So if you look at the example in the book, they're gonna start going through a whole lot of trig identities and foiling stuff out and making substitutions. We're not going to go for that. But there's a little bit of a problem with fininting this. There's an A. You can't type in an A. So if you needed to finit this, what would we need to do?
Alpha math. That's it.
Well, yes, you can type the alpha A. It's going to give you an error. Or it will use whatever, if you've ever used the letter A before and it meant something, it will use that meaning for A. It won't actually give you an answer with an A in it.
Actually, just do it and then multiply it by a.
Yeah.
Square root of a.
Okay, so we could type it in without the a's, which would be like assuming a is 1, and it's going to give us some kind of an answer, right? But we don't really know exactly how that a came into play. So then what would we want to do?
Delete it.
Do it by hand.
If you do it by hand, it's going to take a lot of trick identities.
Can we
Let's not do it by hand.
can we pull an a out for both? Can
Yeah.
we take square root of a times square root of stuff?
Okay,
I want.
so since there's an a squared in both of them, we could pull an a squared out, which would leave us with 1 minus the cosine squared and a sine squared.
Then you can pull it off.
Right, now I can pull out that a squared, take a square root of it, and I've got an a out front of this whole thing.
Why is minus then?
Yeah. Why did you take the square root of it? Oh, got it.
Because there's a square root.
Chef Nancy.
I want to say.
Okay, so now we could finite that and just multiply our answer by a.
Can't you just square root everything and take the square root?
Again,
We can't take the square root of each of them because of that adding in the middle.
Negative cosine plus sine, negative cosine of t squared plus sine squared of t equal to -1.
You're just squaring each part, which is not what we would want to do. We'd have to actually FOIL this. 1 minus 2 cosine of t plus cosine squared t. Now you guys are making me do the trig identities. I said I wasn't going to do them. Here's a plus 1. So now this whole thing turns into the square root of 2. That.
Okay. Which I have no idea what we could do from there.
George, there's an even better way to do this. It's called dough.
Thanks.
The book actually goes through all these identities and gets it down to here and then says, finite it. Because you don't have a way, really, a great way of integrating something like this. We could try some substitutions and stuff, but I actually think everything that you know about how to integrate is going to fail on this problem. So we have to finite this guy. What my suggestion was going to be with how to deal with the A, instead of doing the algebra and taking the A out, would be, since you'd have to have a calculator on this thing to finite it in the end anyway, plug it in without the A, which is like pretending A is 1. It's going to give you an answer. The answer it's going to give you is 8.
Yes.
Then go back and say, well, what if A was 2? What would it be? Plug it in, and the answer is going to give you a 16. I'm willing to wager a pattern on that. But if you're not willing to wager a pattern on just 2, which is not a great idea, then go ahead and plug in 3 and see what you get, and it's going to give you 32. And I'm going to start to bet. Oh, it's not going to. It's going to give you 24.
I was going to say, now I'm more disturbed by my past.
It's going to give you 24.
Are you adding?
And so I'm willing to bet now that what we're doing is just multiplying by A.
Yeah, are you?
Yeah. Yeah. All right, that's the end of 10.1.